introduce Kevin. Kevin is in Toronto. He's based on Toronto. He is part of Lightband, previously TypeSafe, and he runs a meetup called Reactive Programming Toronto. I'm going to pass it to Kevin, and Kevin is going to introduce Dean to you, and Dean is going to start the talk. Thanks.
Thanks everyone for coming out. This is awesome to see the turnout in spite of the awful weather. I was a little worried. I mean, really what we're trying to do at Lightbend is just get a lot more speakers, really great speakers like Dean. So first off, I just want to thank Dean for coming in. I've been trying to get Dean up to do a talk. I want to give you a little bit of context on Lightbend, formerly TypeSafe. As of 2 days ago, we've changed our name. So we're the corporate steward of Scala. And we have other tools like Play and Akka. Spark itself, for those, how many people are not familiar with Spark? Like, do we have anybody really new to the Spark ecosystem here? For anybody that's not aware, so first off, awesome, thanks for coming out. We want everybody to come out to these. But Spark itself is built in Scala. So at Lightbend, we've actually started a big data architecture team led by Dean, who is a member of the office of the CTO at Lightbend. So really what we're helping to do is sort of twofold, is we're offering support to Spark developers on the development side. So leveraging our Scala knowledge to help people who are building production systems. And on the other side, we're contributing to Spark. So we've actually contributed Backpressure to Spark streaming, and we're diving deeper into the tool. So on sort of a related note, I'm local to Toronto. I run the Reactive Programming Toronto Meetup. I'd encourage everybody to come out. I'm actually also running a book club, so functional programming in Scala. So for anybody that's getting into Spark but newer to Scala and wants to kind of dive a little deeper into the language itself and learn a little more about functional programming, we're running through a book called FP in Scala right now. So we meet every Monday, and we take a chapter of the book, and we're going to keep starting it over every time we finish it until everybody's happy and wants to move on. So yeah, check it out. It's a deep book. Anybody that's, how many people have read FP in Scala? Is there anybody that's going through that? Yeah, how many people found it a little challenging in the beginning? Okay, awesome. So we're up at chapter 6 or 8 now, and enough people want to do it all over again that we're going to do it all over again. So yeah, I encourage you to come out. And but most of all, thanks everybody for coming out. We want to do a lot more. I want to bring a lot more people from Lightbend out. So it's great to have the turnout. I'd like to introduce Dean. One of the guys I was like, I've been at Lightbend now for 2 years, and one of the guys that I was really to meet, because I've read a few of his books, so I'm not going to embarrass him and tell you all the books that he's written, but anybody that's done any Hive might have read one of his books. Yeah, and like I said, he's part of our office of the CTO and really guiding our strategy in big data. So really, we're really heavily committed to Spark and really excited about the technology. So without further ado, let's get to the talk itself. Dean, round of applause.
All right, just turn this off so I get feedback. Let me finish setting up a little bit here. So I live in Chicago. I appreciate you guys ordering weather so that I feel like I'm at home. I'm very grateful for that. All right, actually one more thing I want to do. I'd like to mirror the slides. Let me fix that quickly. Oh. I said I want to mirror them. I don't want to mirror them, just to be clear. There we go. Okay. All right. A little bit about the presentation. These are photographs from the Olympic National Park in Washington State. Vancouver Island is just off to the right here. We're literally very, very close to Vancouver. I used to live in Seattle. I was back there last summer for some backpacking. And this national park, if you haven't heard about it, has both an ocean front, which is this part, and then there's also some mountain parts. So my view is, if you get bored with the material, then you can maybe look at the pictures and not lose your minds. But I'll let you decide if that actually works. The idea with this talk was, having worked with Spark for a while, having worked with Scala for much longer, having worked in big data for a while before Spark, I started thinking a lot about how is Scala and the JVM in particular, how are they as actual platforms for big data? They're obviously heavily used, but are they really ideal? And if they're not ideal, what's being done to make them better? And in particular, we'll look in detail about what Spark is doing to make it better. So I hope there'll be something here for everybody. I'll walk through some code examples if you're new to Spark. If you know Spark really well, we'll dive into some internals a little bit. So hopefully you'll get something out of this. You can actually get this talk right now from my vanity website, programming.com/talks. Actually, it's a slightly older version, but it's more or less the same. You can spam me at this email address. And I also say embarrassing things on Twitter occasionally. I got fired for once, retweeting once. So anyway, so that doesn't happen again. All right. Oh, and I do want to thank LoyaltyOne for hosting us. I know that they're hiring. They've got their folks over here. So go ahead and interview on your way out, if you would. Yeah, I actually run the Spark and Scala user groups in Chicago, and you guys are much more organized than I am. But I know how I really appreciate it when companies step up and volunteer to host and provide food and stuff like that, because I know it's an expense and whatnot. So I appreciate that. Okay, this is the rainforest, and we'll use it to, actually the pictures have nothing at all to do with the talk. I tried to sort of line them up a little bit, but anyway. There's like a stream that goes with the streaming, but other than that, you're on your own. But anyway, let's talk a little bit about Spark. What is it? Well, it's a distributed compute engine for the JVM. For those of you that have worked in big data for a while, Hadoop was like the thing. It still is the thing. But the initial compute engine was MapReduce, and it had a lot of weaknesses. I mean, it got us started. It carried us forward for about 5 years, but then it became blatantly obvious that we need to go to something more modern, more up-to-date, more flexible, more productive for developers. And that's the industry kind of pivoted to Spark. Cloudera basically pivoted to Spark, and everybody else just ran after them. It's usually how these things work. The key abstraction in Spark is something called a resilient distributed data set. It looks sort of like this schematically, where if I have a cluster, my data set sort of looks like a collection, at least from like the API perspective, that I can iterate through, I can filter, I can flat map, join, etc. But it's actually split into partitions, and those partitions are moved across the cluster, so I can do any processing in parallel. All these partitions can be processed in parallel is the idea. So, how do we do it? Basically volume. If you have a big enough cluster, you can process, in theory, an unlimited amount of data this way. And it's presumed because if we lose a partition, Spark actually knows the legacy of each partition, or the lineage it's called, and it can actually go back and reconstruct a lost partition if, say, a node dies or something. So you don't have to replicate the data in memory to avoid that kind of loss. You can, in theory, go back and reconstruct it. And there are ways to avoid the inefficiencies of going all the way back to the beginning, but we won't get into that too much. I think one of the important things is how it has improved productivity. How many of you have actually written MapReduce code? Yeah, I can see the pain in your eyes. I know. I'm still in therapy, actually. I get all sad when I think about it. I'm kidding, man. It's not that bad, but it was horrible. The productivity was terrible because it was sort of an assembly language for big data, whereas Spark raises the abstraction to things that we can actually map directly to what we're trying to do. So we get these really great APIs, and I'm sort of steering clear a little bit of the SQL part at the moment, although I have it on the slide here. But basically, you get to pick kind of the language you want. I think personally that Spark demonstrates the virtues of Scala better than any other tool I know of. It sort of hides the ugly bits for the most part, and it really shines where Scala can be most concise. Even with Java 8 lambdas, I'm going to come back to this in a little bit detail later, it's still not nearly a great experience. And you could use Python and R if you're a data scientist. And as we'll discuss a little bit later, today you get the same performance, which it doesn't matter which language you're using, which is also kind of amazing. And you can write SQL queries, which is kind of cool. Something that you don't really know you're missing when you're a Java developer is an interactive environment, like just a command line that you can just explore your data, you can try different things, you can tweak your APIs and play with them. And then when you're ready, you can maybe take that and turn it into something production worthy. And if you're a data scientist, you know about notebooks as a metaphor for doing this. And actually a personal mission of mine is to evangelize notebooks for regular developers, because it's really an excellent way to, like put code in, tweak it, rerun it, visualize the results. This is just a screenshot I stole from the famous one, the IPython Jupyter notebook. One that we actually like at Types, Lightbend is, we were thinking of doing a sort of a transitional name. I think it was going to be like Type Light Safe Bend or something like that, but we kind of decided that would be confusing. Anyway, we kind of like Spark Notebook because it's actually written in our technology, Play and Scala, and it's actually got a lot of nice features. But anyway, that's whichever one of these you pick. I'd really encourage you to try a notebook if you're a developer and if you never tried one. It's different than what you're used to, but it's a really nice way to work. Okay, I thought I'd walk through an example. This is Moss. That example would be the inverted index. So everybody does word count. Inverted index is just a little bit more sophisticated, so it's not as boring. But just to give you a flavor for what a Spark program looks like and how concise it can be, I thought I would walk through this quickly. So schematically, here's what's going on, and to explain what word count is. I've got these web crawlers that are walking to interwebs, as they say. And let's say I'm finding pages on Wikipedia, like the page for Hadoop or HBase or something. And obviously, there's really more content than I'm showing here, but this is obviously made up. And I'm just going to build with these web crawlers a very simple starting index, which will be like some URL for where I found the page, or maybe some ID that represents the URL, and then the contents of it. Just one record with just the entire contents, maybe stripped of HTML tags, maybe not, whatever. And then some miracle is going to occur, and I'm going to create the inverted index, which is I'm going to take what was the value part, which was the text. Maybe I should kind of do it this way. And invert it. I'm going to tokenize into words and then create an index with the words and then a list of all the URLs where I found that word and the counts. And the counts are important because if you're doing a web search or even a document search with Elasticsearch or something, you probably don't want to find the documents that use a word in passing. You want to find the documents that are obsessive about the word. If I'm searching for information about Spark, I'd like to find stuff that really talks about Spark. So we need to calculate, that list of URLs and then the counts on each URL. And just to zoom in a little bit so you can maybe see it in more detail. In my little contrived example, the counts are all 1, but nevertheless. All right, here's the actual Spark code. As you'll see in a minute, it actually fits on a slide, but I blew it up a little bit so it could be easy to read from the back of the room. You always start, this is Scala, but it's kind of like Java. You do some import statements. The Spark context is your entry point. It knows how to connect to your cluster or whatever you're doing. It's also the hook we'll use to read files and so forth. We'll instantiate one of these Spark contexts. The master could be local. When I'm just doing stuff on my laptop, it would be implicitly local if I were in a notebook, but then I can take this code, turn right around, change that master argument, run it on a massive Hadoop or Mesos cluster at scale when I'm ready to go to production. So I create one of those things, and then I'm going to start reading in data. And in this simple case, I'm going to assume that it's comma-delimited data, text data. That's not the most efficient way to store stuff, but it's convenient for learning. And when I create what I call text file on Spark context with the path to my input, I will have created my first RED, where that bracket string thing means that the records are just of type string. Like if you, in database terms, I have one column, it's a string. That's actually each line from the file, basically. And then the next thing I'm going to do is map over each line. And by the way, everything from here, where I started this pink rectangle, to the end is actually going to be one expression. I'm just going to do method argument dot method argument dot method argument. You don't have to do that, but just to show you how concise things can be if you're not used to writing code this way. Anyway, I'm going to map over each line. I'm going to split it on the first comma so that I separate out that URL from the text, assuming there's no commas in URLs. I don't think that's legal, actually. Maybe I'm wrong. And then what this little expression means is I'm going to return a 2-element tuple. Anytime you put something in parentheses that's not like an obvious method call, it just creates a tuple of whatever arity you said. In this case, it's 2, first element of the array, second element of the array. Flat map is a sort of a generalization of mapping, where mapping is always one-to-one. So the first thing I did, actually, if I started with, say, 1,000 records, I ended up with 1,000 records. Now I'm going to tokenize that text into words, and so for each record, I'm going to output 0 to many new records, and flat map lets me do this without going into a lot more detail. So it's 0 to many for the output. So I'm going to pattern match on the tuple. This is something I love about Scala. It's like my favorite feature. I can pattern match on the tuple I just created, assign variable names to each piece, and then just work with them. So it automatically tears it apart, assigns each piece to an argument, and I don't have to do any sort of like getter setter stuff like you would have to do with Java. So anyway, I've got the ID and contents. I'm sort of hiding what 2words does. You know, I could use some fancy string tokenizing library if I wanted to, or split on white space if I'm sloppy, whatever. And then map that resulting array or whatever comes out to, notice this tuple, for those of you on the other side of the room. This tuple, I have a nested 2-element tuple and then an outer 2-element tuple. The nested 2-element tuple is going to be my key. It's going to be each word and the ID, and then a seed count of 1. So I'm going to start counting by putting a count of 1 for each of these. And actually, the next line, the reduce by key, this is really like group by, but it's highly optimized, because I don't really want to build up like these long groups for each key. All I really want to do is find out how big each group is. So I'm going to group over the first thing, which is that word ID pair, ID being like the URL. And then just by adding up, this is a very shorthand way of saying, just add up the integers, underscore plus underscore. You don't have to write it that concisely, but man, is it handy. And that's going to add up the integers. So the output is going to look something like in the white bubble, or now I've got records that are like a tuple with a nested key tuple, and then these nested tuples and counts that could be 1 or more. Okay, this is my favorite line in this program, and the reason I love this line so much is I'm doing this pattern match where I'm reaching down inside this tuple and ripping it apart, and I'm just putting it back together. It's like I'm just moving the parentheses. Imagine doing this in Java. You'd have to instantiate like a Spring factory, detuple, tupulator factory, manager factory in order to do this. But here in Scala, it's, you know, you think what you need to do and you just write it and you're done. That's what I love about this. Now here at the end, we actually do have to do a group by, and what this group by key will do is it'll take the first element of the tuple as the key. And so now we're really getting all of those URL counts together for each word. And I'm actually done at this point. The last step is just reformatting. And in this case, like I said, I'd like to sort by count. I want the high counts first. And so I just kind of hid the details with this sort by count method. But really all it was doing was reformatting output. And then save as text file. We'll write it back as text to wherever I want, HDFS or S3, whatever. So it does actually fit on the slide. It's a little bit small, so that's why I broke it up like that. Whether you followed all that or not, I hope you could appreciate that you've suddenly taken what are typically software engineering, projects where I've got to throw it over the wall to QA, and I've got to have a big design document and draw UML and all this stuff, down to a script. You could run this in the Scala shell if you want. You could run this in a notebook. You could put it in a Scala program if you want, which is what you typically do for actual production deployment. But look how small that is. You write this in, the first time I wrote this, it took me 30 minutes because I knew the operators, I knew the Scala. And then I could just play with it, tweak it, decide, oh, I forgot to sort by X, and do all, I'm going to make this a little faster, that kind of stuff. But I just love working like this. So I said earlier that Spark raised the bar for productivity. It also raised the bar for fun. Suddenly, I wasn't needing that therapist anymore. I could actually enjoy my life. And so for me, this has been a real transformation. Okay, what about performance of this thing? Well, it turns out that all of that stuff that I did was actually just laying pipe, is the way I like to put it. I'm just defining a data flow. I'm setting it up. Nothing actually happened until I said save as text file at the very end. This is actually a lazy API is sort of the term that you'll hear people use. It is inspired very much by the Scala collections. It was very easy for me to learn Spark, at least to get started with it, because I already knew the Scala collections. There's some significant departures, and especially as we talk about DataFrames in a minute, you'll see some more. But I knew these operations. Like basically, I just kind of reproduced them in the little bubbles there. I knew how to use all those things. So when I sat down to think about how would I do inverted index, I could start to break the problem down into steps, and then it was just very quick to just roll them out. And like I said, it took me 30 minutes. And I'm not trying to brag in any way by saying that, but when you have the right tools at your disposal, it's amazing how productive you can be. Well, so what you're actually doing, though, is you're defining a directed acyclic graph for all of your computer science majors of steps. And then when you actually ask for results, Spark will figure out, all right, he asked for results here. What do I have to do back up at the beginning to get to this point? And then Spark will run that, and it runs it over a cluster. The other thing it does in terms of optimization, and we'll see a lot more about optimization as we go, you might think, oh gosh, this could be really inefficient if I'm doing like terabytes of this data and it's building up a RDD at each of these steps. I didn't really say this, but each of those methods is returning a new RDD. That could be really inefficient. These are not mutable things, they're immutable. But it turns out Spark doesn't do that. It doesn't materialize all the RDDs. It only materializes RDDs when it has to produce something to send over the network, to write to disk. The ones I've highlighted, it turns out whenever you do something that's like a join or a group by, that's when you have to shuffle key value pairs across the network. And at that point, you have to materialize the RDD. But it can pipeline the previous steps together. So when I was doing like map, flat map, and filter kind of stuff, it can just, as each record goes through, it can just call the methods, just on each record without actually instantiating anything intermediate. So it's pretty efficient in that way. And these are called stages when it figures out, where it can break things up. And if you look at the output of the Spark web console as it's running your job, you'll see how it's running these stages across the cluster and letting you look at statistics and stuff. Okay. Well, I kind of blasted through that really quickly. Let me go back. Here we go. So one of the advantages of a really good abstractions at the core is that you can layer on top more interesting semantics to address more particular kinds of problems. Now, as many of you may know, and the fact that you have a Kafka meetup here now is indicative of this, that people really care about streaming today. They want to be able to get answers faster, not just collect data and then run a big batch job every hour, day, whatever. Spark, unfortunately, perhaps, started as a streaming engine as well as MapReduce. It started that way. But because it's relatively efficient, they realized they could apply this clever hack. And it really is a clever hack where, well, what if we just had really short batches? Like, let's say down to a second. You collect data for a second, we'll run a batch job over it. And while that batch job's running, we'll collect the next second's worth of data and so forth. So it's basically a mini batch streaming model as opposed to a low latency model where you're just going to handle every event as it shows up. It turns out this does actually make Spark a lot more complex in its streaming engine, and this is actually an area where TypeSafe has helped working on hardening of Spark. Lightbend. It's a good point. Very good point. Yeah, time-wise, it was it was TypeSafe at the time.
Buys drinks for all of us every time.
Yeah, we'll have to do a drinking game. Yeah, first person yells bingo gets a beer. Anyway.
Did you mean to say that Spark started as a streaming engine or a batch?
No, I really meant as a batch engine. And then they're basically doing this hack. I should show you this slide where I'm going to define, me being the user, I'm going to define these time windows. And unfortunately or fortunately, depending on your point of view, they have to be fixed. I have to decide up front, all right, how often should I actually process this data? So as I sort of alluded to, like a second is sort of the minimum time interval, which is horrible if you're like building a flight control system. If this is not a real-time eventing system by any means. And it could actually be, it's unlimited in the size. If you don't mind having memory, or rather data sitting in memory, you could have batch intervals that are hours even. That would not be a necessarily good idea. And you can also define windows over them. So you could do things like, let's keep moving averages. We're going to maybe every 5 seconds do something but we're actually going to keep running statistics over the last day. You can do that kind of stuff. But anyway, so I define this time interval, and then how many ever events show up on my stream. You know, here I'm showing like 3, then 5, and so forth. Actually, I said that backwards. Anyway, I'm going to capture those events and then run my batch job over them. And that's the idea with Spark streaming. Now, there is actually an advantage. I said there's some disadvantages. The advantage is if you make these intervals wide enough, then you can do all kinds of very sophisticated calculations. You can do machine learning on this stuff as it's coming in. There's some really nice examples that come with Spark doing streaming k-means, where I'm just going to calculate the clusters over each batch. Or I can do like logistic regression. I can update my model and at the same time make a recommendation on the data that just came in. So cool stuff like that is possible. A little harder to do if you're doing a low latency streaming engine. So to cut to something I'll say later, one way that you might end up pairing a tool like this with a low latency engine is if you really need that sort of low latency event handling, like fire alarm handling, that kind of stuff. Use one tool for that. But if you want to do more sophisticated stuff where the latency is less sensitive, then use something like this. So you have that option. Well, I mentioned that there's some potential robustness issues with streaming because it's fairly sophisticated. I really love this slide, actually. So the patterns that the sort of teeth, the receding tide made around this seaweed were really cool. Anyway, so here's a problem. And you should keep this in mind if you're thinking about going from batching to streaming. You know, if your batch jobs, they might run a few hours, maybe. Maybe you do something overnight, like you process, starting at midnight, everything that happened in the business the day before, and maybe it finishes at 3 a.m. If it fails, you restart it, whatever. But when you start a streaming system, it may run for months, maybe years, maybe you never intend to turn it off. So you've sort of raised the bar on your challenges. Not only mundane things like how am I going to update this thing when I decide to change what I'm doing, but you know, anything that's rare becomes commonplace when you wait long enough. My favorite example of this is places like Google. They're replacing hard drives all day. Most of us don't replace hard drives anymore. Our laptop hard drives are actually really good. How many of you have actually replaced a bad hard drive? A few of you, right? But if you were a Google Ops guy, you'd be doing it all day long. In fact, I've heard they don't even screw them in anymore. They're like Velcroed in, so they just rip them out. But it's the same thing here. If you wait for months, any weird thing is going to happen. Like some node is going to act really, really wonky and suddenly slow down its ability to process. Or you'll hit, maybe a Black Friday. Let's say a Black Swan Black Friday kind of thing, where suddenly you expect this amount of traffic, the day after U.S. Thanksgiving or whatever is equivalent up here. And then all of a sudden, for whatever reason, you do this sale that happens to be really popular, and you get 10 times the normal traffic. These kind of things happen. So what are you going to do if your system is only designed to handle a certain load in a streaming context, other than crash? I mean, you've always got that option. You can always crash. Most of you probably would say that's a bad idea. So this is really cool idea. It's not new, but it's something that we've been trying to popularize, which is backpressure. And actually, it's not new because this is exactly what TCP does. If you push too hard on a TCP consumer, it pushes back and basically slows down the flow rate. We actually added some code to Spark in version 1.5 to implement a backpressure mechanism that actually measures its ability to process the data as it runs, and then dials back, basically uses TCP backpressure as of this version, so that it doesn't get overwhelmed. If it did get overwhelmed, it would look like this. This is a graph a colleague of mine did. Let me explain what it's doing. So the green bars, each of those bars is like a batch iteration. And the height of the bar is basically the amount of data that it's receiving. It's actually sort of a proxy for the amount of data. It's the time it takes to process the data. Now there's a line that most of you may not be able to see. There's a little dotted line near the bottom. That's the batch interval. So you can see that when we suddenly doubled the amount of traffic, then it could no longer finish processing the last batch before the next batch was ready. And what Spark does is it's like a queue. It just waits for that guy to finish, and then it will start processing the next one. So these red lines are actually the so-called scheduling delays. This is exactly what you would see in the Spark UI if you were watching a system like this run. So you can see it's forming this rather pretty triangle. But actually, this is really bad because eventually it would run out of memory. It's probably what would happen first. So what my colleague did is you can see that on the sort of the right-hand side here, we have this convenient dividing line here today. He dialed down the rate, just manually, and then suddenly it slowly recovered. It slowly caught up and then got back to normal. This is what happens in Spark as a version pre-1.5. And once again, this is the sort of thing that's very typical behavior that you could see for a wide variety of reasons in a streaming engine, and you do not want to see this ever in a streaming engine. So what do? Well, the simple mechanism we implemented is basically it's actually watching how fast, like I said, how much data did I just get the last interval, how successful was I at finishing on time, and if I've hit that tipping point where I'm not keeping up, then it actually pushes back on the stream. So you can see there was a transient phenomenon here, a similar setup scenario, where it did start to fall behind, but then we pushed back on the amount of data, so you can see that the green started to have this little dip, and then the red caught up. The delay eventually went back to 0, and it sort of reached this equilibrium point that would notice, if you can see it, the dotted line, it's basically oscillating around the dotted line at this point. So that's that's the backpressure mechanism we implemented, and again, all it does actually is look at what's happening inside the context of Spark. What you really though want to do in any system like this is actually have a dynamic mechanism that's communicating between the producer and the consumer to adjust the rate. And that's exactly what the Reactive Streams standard is all about. I really need to do this. I should put this API on a slide. It's a very small Java API, and it's really about establishing a protocol for producers and consumers to adjust the rate of flow. It's actually a push model when the consumer can keep up. It flips to a pull model when the consumer is running behind, and then it can go back and forth. So what we're actually working on is the ability to hook up any reactive stream to Spark. This will probably be in version 2.0 of Spark this summer. So you could hook up an Akka stream to it, an RX Java stream. I think someone is working on this for Node.js. And the cool thing too about this model, and it sort of looks like this, where you have this back-channel mechanism of communicating from consumers all the way back to producers. This actually composes beautifully. So if I have like a graph of these things set up, as let's say that the far end on the right is falling behind and it pushes back to its immediate producer, that can in turn push back to its producers and go all the way back. So it lets you make strategic decisions about flow control, and strategic in the sense of, at some point you're going to have to decide what to do, but hopefully that point is right at the ingestion point of your application, and then you can make strategic choices like, all right, I can just drop data at this point. It's actually not important that I keep this data. Or I can maybe flush to disk and then process it later. Rather than having some little socket down in the middle of your code, just with no context whatsoever, make a decision about what it should do. And that's what you're trying to avoid with a model like this. Okay, so things like this are being done in Spark streaming to make it more robust, to be able to run for maybe years and never die, which is pretty important. So that's one model that we can build on top of the RDD API. One of the more exciting ones, well, streaming is exciting, but one of the interesting ones in terms of engineering is this SQL or DataFrames module that they built on top. So SQL lets us write SQL queries, and there's going to be a query optimizer under the hood that's going to optimize your query. The DataFrames is really like a programmatic API for writing SQL queries, and it's a little bit more type safe than just a SQL string and SQL query embedded in a string. You'll see what I mean in a second. This slide is slightly off. So I say it wraps RDDs. That's technically correct. But what we're going to see in a little bit is that they're doing some kind of amazing engineering inside to make this a much more efficient engine than the RDD API. So for those of you that are learning Spark and maybe starting to use it at work, if you can, use the RDD API because the performance is drastically better. That's the RDD, sorry, back up. Use the DataFrame API because the performance is drastically better than the RDD API. There's some things you can't do in the DataFrame API. The inverted index, I think you can. But so sometimes you have to drop it down to the RDD API. But in general, prefer DataFrames. So let's look at an example. I'll start with some setup code here, and let's zoom in again. The usual Spark context, now there's a SQL context that I wrap the Spark context with. There's some really nice I/O libraries for doing things like reading and writing Parquet. Parquet is a very popular columnar format for file systems now. Those of you that have done any Hadoop have probably heard about it. Also JSON, it can infer JSON schema if you want to ingest JSON data. There's plugins for CSV files and so forth. So I'm going to load this data set actually, and I'd be happy to share the source of it. It's a collection of all of the airline flights, commercial airlines in well, I think it's actually just the US for the last like 15 years. So it's actually fun to play with if you travel a lot like I do. It's actually shocking how many flights are canceled in the US. And you can imagine most of the cancellations are like December 24th, for convenience. Anyway. So what we can do is we can load this data. The Parquet actually has the schema already. So the flights and the planes objects are data frames, and they already know their schema. I can register them as temp tables in sort of the databasey way. So I can write SQL queries, and here's one of them. So this is just a very simple query where I've got some data about planes, like the year they went into service, the model, that kind of stuff. I'm going to join that with the flight data, so I'll just have like a list of all the flights and then all this data about the planes that actually flew the flights. So hopefully all of you, how many of you have never seen a SQL query before? Anybody? Okay. I was going to throw you out if you didn't want to see it. No, I have to admit, so here's a little confession. I was sort of a typical Java developer back in the day, when I had less gray hair, let's put it that way. And I kind of thought, databases, they're so awful. They're not perfect object models. I want to get that data into my beautiful in-memory object model. I don't want to mess with SQL. I don't want to mess with DBAs. But actually, it was when I started doing big data that I really appreciated how beautiful SQL is for getting stuff done in a very concise way. And I love the way that, like Kevin mentioned, I co-wrote a book on Hive years ago. I just love the way that you can kind of mix this wonderful, concise metaphor for asking questions with a very flexible environment like Hadoop. You're giving up a lot, like transactions and that kind of stuff. But for really concise questions, man, there's nothing like SQL. Okay, enough of that. So that's the SQL query. This is the DataFrame code. And, to be honest, it takes a little while to get used to this code because it doesn't quite look like Scala collection. So there's some learning here. But, it's almost as concise as the SQL stuff. I'm basically going to do flights.join, and then planes is the second table. And then there's a join clause. What am I joining on? And I'm going to look at that just a little bit more here. So the first argument that I've sort of grayed out again was the second table. And notice this expression, flights, tail num, triple equals, planes, tail num. That's actually a little mini domain-specific language in this API. And this is actually very crucial for one of the reasons that DataFrames are so important. It turns out a problem with anonymous functions in Scala, and this is true in Java 8 as well, is that by the time the underlying runtime gets that function, it's just an opaque blob of bytes. The only thing it knows about it, it's actually encoded as a Java object, these anonymous functions. All it knows is the type signature of the function, like I'm converting the string to a tuple or whatever. But it doesn't know anything about what it's doing, and hence there's no possibility for like a tool like Spark to actually optimize what that function's doing. This is actually building up a little abstract syntax tree. What flights and tail num means is it's a one way of selecting the tail num column out of the data set. Same for planes, and there's other ways to do this. And then triple equals, if you don't know Scala, there's a way, it's actually operator notation, but it's just a function call, or a method call rather. So I'm actually calling methods on objects, and I'm building up a little AST for this query, and then Spark can do very aggressive optimizations on that little blob of code that we'll come back to in a minute. And this is one of the reasons why you should use DataFrames when you can. It's a classic example, actually, of if you constrain your flexibility, limit what you can do, then it opens up a lot more options for internal optimization. And it's just a classic example of that trade-off, actually. So once again, use the RDD API if you need real flexibility, but if you can use the DataFrame API, you'll get a lot better performance. we're talking orders of magnitude better is sort of the direction they're headed. All right, just very quickly to finish, there's two other big modules on top of the Spark core RDD API. Both of these are actually also migrating to the DataFrame API. The first one is the ability to do a bunch of sort of conventional machine learning models like k-means, logistic regression. There's actually, this is a rich area of third-party contributions. The Spark project is kind of slowing down the contributions they'll accept for inclusion in Spark. So most of the time, you'll probably want to be good at Google to find machine learning libraries for Spark. Like, for example, IBM has a nice one called SystemML that they've open sourced. And then if you know anything about graph algorithms, it turns out a lot of the data we work with is like graphs. Like this is a picture of the famous PageRank algorithm that Google used to become billionaires. But it's also things like your social networks, you know, your friends, they all form graphs, and being able to use actual graph algorithms is a nice thing that you can do. Okay, so that's sort of the basics of Spark. Let's go back now and talk about, all right, what have we learned from this? What does it say about you know, the tools that we're using, and what can we improve on them? Actually, I think this is my favorite photo right here. Unfortunately, it's cut off a little bit, but this is one of my friends. That little blob in the middle. And this rope here, this is one of those big ropes that they use to like tie ships to docks. There was also, it's kind of sad how much trash was on this beach, and a lot of the trash was actually from Japanese fishing boats after the tsunami, it turns out. So we found a lot of floats and stuff like that. Anyway, enough of that sad story. So what about the JVM as a platform? Well, obviously, the reason that people like Doug Cutting, who created Hadoop, and everyone who's writing like Kafka and so forth, the reason they picked the JVM is because it is actually a really good platform for massive scale enterprise apps. You know, we've got some basic tools we all work with. I threw a bone to Clojure here with the little circle icon. And actually, the libraries that I'm listing are Scala APIs that I particularly like, without going into much detail. I should mention, actually, if you grab the slides, I have links to a lot of the stuff here in the speaker notes. Very important concern is that we know how to run these things. We know we've got 20 years now of actually running JVMs. We know how to monitor them. We know how to tune them. There's a lot of people who can write Java code and can learn Scala. And of course, now we've got the whole data science community, excuse me, coming over. So it's a good platform. And as a result, you know, here's some of the icons I found. There's plenty more I could have added. The most important ones today, as far as kind of this movement towards streaming architectures, are Spark, Kafka, and Cassandra, but there's obviously a lot more here. However, it's definitely not perfect. There's definitely some issues with the JVM, with not just Java, but the actual JVM as a platform that we've had to find ways to work around, and there's some ways in which hopefully Java itself will improve in future versions. Some of the things I'm going to mention are actually planned. How many of you have ever seen a garbage collection pause? All right, anyone who's running operations, I've never seen garbage collection. Child's play. I think the world record that I'd heard of, somebody had like a Hadoop file system, HDFS, that like garbage collected for hours. So I forget the exact number, but it was unbelievably insane long amount of time. The problem is that these big data tools typically have heaps now that are tens to hundreds of gigabytes. And in fact, Amazon is planning to roll out terabyte RAM nodes pretty soon. I don't think they're quite available yet. The JVM was never designed to run heaps that big. And that's very unusual too, because most of the services we build today, whether they're microservices or macro spaghetti services, it's rare for heaps to be anywhere near this big, but it's all data, right, that we're stuffing in these heaps. And that's the secret to the solution. If most of this is actually holding data, then maybe we can do something radical to fix it. Well, it turns out if you naively load even like those tuples I was using for inverted indexes, then you could just get a ton of garbage. Imagine you had 1 trillion of those records and they were all in the heap, and now I had to garbage collect them because the job just ended. I've actually, even on my laptop, I've seen Spark jobs that, you know, I hit Control-C and it takes like 2 minutes to actually stop. And I think it's just actually, you know, trying to clean up after itself. Although kill mine works a lot faster, I found. handyman's secret weapon after duct tape, I guess. And part of the problem is that, you know, our traditional garbage collectors weren't really designed for these very small but very massive number of objects. Well, just a little, if you're actually trying to tune your, the next two slides are like advice if you're trying to tune your Spark instances. This garbage first GC is the thing you want to use. It actually structures your heap more in these little small objects. And without going into a lot of detail, here's the flags you want to use, and go to this URL. Actually, if you don't want to look at the URL and you don't want to look at the slides, just go to Databricks, Google Databricks and GC tuning, and you'll come up to this amazing blog post that some engineers from Intel wrote, where they found like the perfect combination of GC flags for Spark as a pre-1.5, and I'll explain why that's important in a minute. Well, it turns out a lot of what we can do to fix our problems has to go really go back to the Java object model itself. It's wonderfully flexible. We've used it now, you know, very well for 20 years. Spark, Scala's using it too, but it really is not optimal for data. So, for example, if you see this string ABCD, you might assume that it's 4 bytes. Anyone want to guess how many bytes this actually is in memory? I heard 8. And why did you say 8? Yeah, it's actually, well, that's the first thing. It's actually 8 because it's UTF-16. But there's a lot more than that. Anybody want to hazard a guess? It's actually 48 bytes. It's a 12-byte header that every object carries. It's 20 bytes for the array overhead because I'm storing an array. And then it's 8 bytes for the UTF-16 characters. I think part of the 12-byte header is also the hash code is always calculated for objects. So I'm actually carrying a lot of data or a lot of overhead for what is actually a very small bit of data. And again, multiply this by 1 trillion and you've got a problem. Ah, there it is, 8 bytes for hash code. I guess I didn't go far enough. The other problem is all these little arrows I'm about to show you are cache misses. You know, I allocate this array, and unless I'm allocating like an array of integers where it's all going to be contiguous in memory, each of these array indices or array elements is going to actually be a pointer in memory to some other allocated object. So if I'm ripping through this array to process the data, chances are it's not on my cache lines in the CPU. So I'm going to have cache misses. I'm going to go out to memory to fetch this data, and it's enormously expensive. Same for, you know, typical class instances, you know, like this fake little person type. You know, I'm pointing to a string. Once again, this is, you know, way too expensive. I'm pointing to some sub-objects. Hash maps are used a lot, both by, you know, in application code, but also internally to Spark. And, you know, every key value pair is, you know, that's together, but then it's pointing to key values and it's a linked list. All of this stuff is overhead. I mean, it works great in the general case again, but for data, it really adds up. The other thing we've discovered experimentally, which is a new compared to MapReduce, is that Spark jobs are typically CPU bound. That there's some interesting research done by this at Berkeley. If you improve network I/O, you'll only see a few % increase in performance. If you improve disk I/O, maybe 20%, like, you know, switch to SSDs. So if we're going to actually improve performance by orders of magnitude, we have to improve what happens at the CPU level. It's actually interesting to look at why this is true. One reason is that hardware has actually improved a lot since the early days of Hadoop. You know, now we typically deploy 10 gigabit Ethernet networks in our clusters, whereas it used to be like 100 megabyte a bit or whatever. We're using SSDs more often, so hard drive I/O is a lot better. And Spark tries to do smart things like pruning unneeded data sooner. For example, one advantage of using Parquet is that if you write a query that selects just a few columns out of all of the records, it only reads those columns because they're stored in columnar format. So you're actually leaving a lot of data on disk that you don't need to read into memory and then throw away. We're also, you know, Spark tries to use caching more effectively, and we have these data formats like Parquet. Parquet also uses compression, and so that also reduces disk I/O. Oops, wrong key. And because we're doing serialization, because we're doing compression more, because we're hashing stuff a lot for like joins, that actually increases CPU use. So how are we going to fix this? Well, it turns out that this is where they're working on the DataFrame API. I have been working to improve this performance. When they rolled out the first version, I think this diagram was taken from Spark 1, maybe it was 1.5, I think it was like 1.4 something. Just by the initial optimizations they made that we're going to get into, they were able to double the performance of Scala over the comparable Scala RDD. But notice what happened with Python. They took the Python code to be about, almost 5 times fast. No, I guess it's 4, a little over 4 times faster. And notice that the 2 green bars are the same length. This was the first example when they were able to actually get Python to run as fast as Scala. So as much as I love Scala, as much as I don't really like working in Python, if you're a data scientist, you don't have to throw your code over the wall to your Java developers anymore. You can run it in production at the same speed if you're using the DataFrame API. Here's some of this is just a laundry list of some of the methods, and if you actually read these carefully, and I'm not going to go through this, but if you just like scan a few of them, they should look very reminiscent of SQL operators. And this is again the DataFrame API. And you'll notice things like, here's that join that we saw the first time. Notice that here, we basically pass this expression that resolves to a type called column, and that's just their encompassing type for that little AST that's going to tell me how to join 2 things together that I can then optimize. So we saw this earlier, that's not an arbitrary function I'm passing here. It's actually one of these column instances which gives them the ability to reach in, look at what I'm doing, and then optimize it. And all these optimizations are part of an ongoing project called Tungsten, where they're trying to really dramatically improve this performance. And they're planning to work some of this back into the RDD API, but most of it they can't do. So we want to fix 4 problems. We want to get rid of all of this Java object overhead, like the 48 bytes for an array and stuff like that. We want to reduce GC pressure. We want to minimize cache misses. And we also want to minimize function overhead. Now, this one was surprising when I saw this. Those of you that know much about the JVM know that, like, if you have a class hierarchy with a method that's overridden in subclasses, the JVM is really smart about knowing when it can inline even these polymorphic functions. And it actually puts in logic where if it guesses wrong, it will back out and do the regular indirection. It turns out that's still expensive. When you're doing it trillions of times, everything adds up. So they're actually trying to get rid of all of that kind of overhead and just generate raw code that's as fast as possible. Like as if you had handwritten the code for those little expressions we just saw. So we're going to get rid of some of these arrows. We're going to use, instead of having lots of little objects, we're going to have lots of big byte arrays, and then garbage collection is like really fast if you're just deallocating a relatively small number of big things. And we're going to try to line up this data so that it just fits in cache lines so that I don't have to miss the cache so much and don't have to go to memory. And then finally, when I have expressions like, I know that some of you in the back can't see this, but if I write a SQL query, like select A plus B, or use the DataFrame API, then I can turn that into the optimal code, like getting rid of virtual function calls, eliminating any boxing and unboxing. That's when I convert like a primitive integer to a Java integer, that kind of stuff. And also eliminating if statements, if I can do that. And what they're doing is they're actually generating custom byte code in the runtime when this happens. Okay, so let's look at what they're actually doing to address this. I'll just skip this slide because it's kind of what I already said. First of all, how many of you have heard of sun, miss, unsafe, that API? A few of you. How many of you have actually used it in anger? Okay, a few of you. This is like the C programmer's best friend if you're forced to write Java code, because it basically gives you malloc and free and some other things. So what they're actually doing is going off heap. Instead of using the regular Java allocations, they're actually doing this in a custom way. So they've introduced this new compact row type where any record that you write is going to follow this sort of algorithm for laying it out in a single line of bytes. The first field is actually a null bit field. So if the bit is on, that means the corresponding field has a null value. So there'll be it won't have any presence in the rest of the record. The next bit is just one after another, each value in the record, if it fits in 8 bytes. If it doesn't fit in 8 bytes, like it's a string, then it's going to be basically a pointer, a reference, whatever, into this variable length section. So that's sort of the algorithm they're using to lay out these objects in memory, in a contiguous way, so that you don't get cache misses. Excuse me, I get all choked up when I talk about this. They also wrote their own custom Hashmap, which basically lays out key value pairs in just a big blob of memory. This would really suck, actually, if you wanted to do like incremental additions of key values, because you'd have to copy the whole thing every time. But most of the time, the way this is used is I just create this map once and never change it. So it's okay if I just, one after another, just stream them all into a byte array. So when we do this, we get much better cache performance. We also drastically reduce garbage collection because we've reduced the number of objects. And then finally, to get even better performance, they do custom bytecode generation for expressions. Something that's coming, there was a great talk at Spark Summit in New York 2 weeks ago, or no, it was last week. The next step of this is to take entire queries and generate custom bytecode for the entire query. Like even if you use the DataFrame API, you have a long expression that's doing like 3 joins, they'll just generate bytecode for the whole thing. There's some other things they're doing that I've forgotten, but they're actually shooting for another 10x performance improvement. And I think they're already at 5x better based on the nightly builds. Okay, so to kind of get to the end here, the last few things that suck about the JVM is, one, we don't have unsigned types. Like, what is factorial of -1? Anybody want to answer to guess? Unfortunately, the type signatures don't let us say it has to be assigned. And that also sucks if you're trying to use like a 4-byte object as a bit array, because you have to worry about the sign bit. This is a classic. This is one of those like Bill Gates saying, why would anyone need more than 640 kilobytes of memory in a computer? Why would anybody want more than 2 to the 32 or 2 to the 31 values in an array? Well, it turns out if those are byte arrays, it's only 2 gigabytes. And if you're talking about terabyte heaps, then this is actually a big problem, that we have to index arrays with integers, especially when they're small objects. I don't know if any of you know the tool H2O. It's another sort of in-memory compute engine. I know the chief architect is a guy named Cliff Click, and he gripes about this all the time because it basically became a case where he had to like internally manage all of these smaller arrays just to represent the illusion of a bigger array. Value types are an interesting thing. This is another optimization. Think of it this way. Suppose you're stupid and you use doubles for money, but you wrap it in an object type. And then those of you in finance know that's a really bad idea to use doubles. But you wrap it in a value, some object that has things like, what currency is this, and maybe there's a method to convert to some other currency, stuff like that. What you'd really like to do is write your beautiful code with your money type and then have the compiler automatically just take that, double out of it and treat it as a primitive type, because the compiler will push those on the stack and not heap allocate those objects. It turns out Scala does this now, but you really want this at the JVM level where you could have these elements wrapping single primitive types that give you all the beauty and whatnot of objects, but they're actually allocated on the stack. So you don't get an allocation call, you don't get a garbage collection call. You push it on the stack, you pop it off when you're done, and that's it. Those of you that do C programming or C++ know what I'm talking about. That's actually coming in Java, maybe Java 9 or 10, we're not sure. Finish this list. The fact is, if you're a data scientist, Python and R have just much richer libraries than Scala does. This is something I'd love to fix myself. I know people who are working on this kind of thing, but that's one good argument for using these languages. All right, let me talk just quickly to sum up why Scala as opposed to Java, let's say. Well, the reason I fell in love with it was I thought it was a really pragmatic mix of object-oriented programming, which is great for like modularity, and functional programming, which is great for correctness. And I kind of think of big data, and I think Spark exemplifies this as sort of a big sandwich, if you will, where I might, if you're looking at scopes from the outside in, I might use objects as modules, and like RDDs are sort of like objects. I want to use functional APIs to manipulate everything because I can reason about them and I can test them easily. But maybe internally for optimization, I might even use mutable code or crazy stuff like I just mentioned they're doing with Tungsten. Could not live without the REPL. If I went back to Java, I'd probably kill myself by not having a REPL, because for me, it's the way to explore and discover. And notebooks just make it even nicer. The collections API, I think, is one of the crown jewel. Well, if you talk to purists, they'll complain endlessly about how they're implemented, but just the power you get at your fingertips is amazing, and that's what inspired Spark's API, at least the DataFrame one. And I think Spark really did a great job of hiding the internal implementations and giving you the abstractions on the outside, even better than the Scala API did. So for me, it's easy. I mean, you do have to know what's going on eventually for performance reasons and whatnot, but you can really get started very quickly without having to know a whole lot. And lastly, I'll finish by saying, what about Java 8? You know, we got lambdas, which are anonymous functions, and that actually makes Spark code not suck terribly. I mean, have you read Learning Spark by any chance, the O'Reilly book? You might recall, all the examples were in Scala, Python, and Java, and the Scala and Python ones were like, this big. And the Java ones, it's like Java 7, again, Spring, factory template, manager factory kind of stuff. But lambdas actually get rid of that problem, but there's some things that I would really hate to give up, like that tuple syntax I was using. Like pattern matching to, determine what I've got, rip it apart, assign it to variables, put it back together. Excuse me. Type inference gets rid of a lot of noise in code, but still gives you the correctness of typing. Scala is actually really great for writing little DSLs like that, the join clause, as I mentioned. It's really nice to be able to do that in Scala. And then again, the REPL and notebooks. So I tend to wrap up with a nice little sunset picture. So Spark is actually really driving adoption of Scala right now, which is, of course, exciting for us at, what was it again, Lightbend? Anyway, we're calling ourselves Lightbenders. Anyway, Spark has too much technical debt. If you want to contribute to Spark, start writing unit tests. You would do us all a big favor. Spark streaming is rather complex, and it needs to mature some more. On the flip side, I think Scala could really more cleanly separate interface from implementation the way Spark, I think, has done a good job of doing. And I'd love to see Scala adopt some of the operations that Spark has, like, I just collected the ones I like here. Like reduce by key is really nice. And I would also like to see these Tungsten optimizations leak outside of Spark into Scala, into the JVM, etc. I'd like to see these problems with like long indexing or integer indexing converted to long and so forth. And on and on and on. Last thing I'll say, I have to do a little advertising. So we do offer commercial support for Spark on Mesos. That's it's my dumb idea that we should do this. It turns out a lot of people don't really need to do those. So we're supporting Mesos as the platform of the future, if you will. So if you want to find out more about my crazy ideas about big or fast data, there's a link that'll take you to a white paper. Again, you can find this talk at this URL, and you can spam me here. So thank you very much. Any questions? Does anyone want to play mic jockey for me?
Thank you very much for the very nice talk. So I have a lot of questions that I came with, but from your talk, and from your position in Lightbend, I want to ask you, since Tungsten is working on memory hacks, Flink are also doing the same, and H2O apparently are doing something with arrays. I didn't know that. So isn't Lightbend in the position to actually collect the best of all of this and put it into Scala? Hopefully Scala 0.10 where Spark is running. So yeah.
That's a good question. Yeah, so TypeSafe does invest in Scala. That was a bit of a blow up that people thought we were abandoning Scala when we changed our name and so forth. But there's a collaboration between EPFL, the university in Switzerland, that supports Scala, and some of the stuff I think Martin Odersky wants to bring back into Scala. It would probably be like 2.12 or whatever's after 2.12. You mentioned three interesting cases, though. H2O, Flink is a really nice streaming engine in Spark. My personal view is that H2O is fantastic if it fits your problem. And if you're in finance, you should check it out, to be quite honest. I think Flink is going to have a nice adoption. The thing about its disadvantage versus Spark is just the size of the Spark community. You know, you've just got, I think they have now something like 500 people, or maybe it was even 1,000, the last number I saw, contributors to Spark. So it's tough to keep up. So I wish them well, but just be careful that you can get the commercial support you need, or at least that you feel that the project is actually meeting your needs. Anybody else? Yeah, in the back here.
Are you actually running Spark on Scala 210 or 211 right now?
Yeah, I typically use 211. In fact, you can, okay, thanks. You can now get 211 builds off the Spark site. We finally convinced them to start building regularly. You know, Spark 2.0 is coming out in April, and I think they're going to finally flip to 211 as the default, but still compile to 210. Actually, Scala 2.12, I think, is due out this year, I believe. I should know this. Was there a question over here? Yeah. Pete, why don't you wait for the mic there?
Okay. So do we have any progress that support JDBC in Scala 2.11? Because as I know, JDBC only support 2.10, right?
You know, I'm not aware of that issue. I'll go research that, but I wasn't aware that was an issue. It should, and if it doesn't, it's because there aren't good tests for it, because we really do run the builds for everything at TypeSafe and at Apache. I honestly don't know if there's what the problem is. Okay. I think it was somebody over here and then back over this way.
I'm just curious if the windowing API has support for fixed batch sizes. You mentioned it has granularity down to the second. I'm wondering if it has plugins based on the number of events or records.
Yeah, that's a good question. I don't know why they don't do this. There might be a really good reason, but they really have decided to say only, you know, like a fixed time window, or so let's be precise, a batch interval, and then windows have to be a multiple of that size. So there's no way to say, like, I want a window over 25 events or something like that. I personally would find that interesting to have, but there may be a reason why they don't do that. That was just, where did I see the build right there?
So it talks about some of the operations, some of the API interface that you have in Spark, how those are nice operations to have when you're thinking about collections, just in general. So are there plans to have sort of a unified, I don't want to call it collections API, I don't want to call it traversable or monoid or whatever you want to call it, right? Because, jokes aside, tongue-in-cheek humor aside, there really is at least a gap that I've felt where, you have the promise that Spark gives, you want to write your program once and you want to be able to have it run over multiple different data sets and things like that. Mm-hmm. When you're writing your program, you really don't even thinking about Spark as an implementation detail. Right? Yeah. You really want to be thinking about your data as an abstract thing, a collection or whatever, and you want to be able to do some operations on it. So what, if any, progress is being made in that, or is this something which is seriously being considered at Lightbend, or is this something which is being worked on? Is this in the works? Any status on that?
Yeah, that's a really good question. There was actually an initiative 3 years ago to come up with a universal big data API that would be on top of all of these others. And in fact, Google is trying to do this again. They have a data flow engine that has a Java API. I actually don't think it'll ever really gain much traction. On the Scala side, for Scala to add all of those methods, there are actually some design problems that would have to be solved, like joins are really hard to do in a single in-memory instance versus over a cluster. And they would also kind of impinge the ability of these different teams and different projects to innovate a little bit. So I think realistically, it's not going to happen. You could certainly try to stick to a subset that you like. But on the other hand, I would say that, you saw how small that inverted index program was. So a lot of times these things are so small, you actually don't care if you have to throw it away because you didn't really invest that much in it in the first place. So I think that may eventually just kind of dominate, that people just won't care that much about portability as long as the concepts are used consistently, if that makes sense. But yeah, it's an interesting question. It would be nice, but I think practically it probably won't happen. So, over here.
Hey. Can you comment on the new features brought in by Spark 1.6, like data sets? and if you have any knowledge about the future for Spark 2.0, like you talked about Spark streaming. Can you comment about streaming DataFrames?
Yeah. The first thing I would suggest is go to the Spark Summit website, because they've already posted, I think, all the slides. And usually you can read the slides without even the videos to get, like, look at the, to be honest, Databricks always does the best talks. And, well, except the ones I do, of course. But they actually had some really good talks about what's coming in Spark too. So just briefly, data sets is an attempt to bring back some of the type safety that you actually kind of lose with DataFrames. Like, you sort of don't really know what the types of the fields are until runtime, and there's more, more holes that can fail. I think it was kind of a half-baked effort in 1.6. You don't really get that much benefit yet. But what they're going to do in 2.0 is actually, so right now data sets are kind of sitting on top or maybe sort of off to the side of DataFrames in sort of an object-oriented way. The way they're going to change that, this is a breaking change in 2.0, is that DataFrames will just be data sets where the type of the record is this Spark row type. So if you use your own case class as the record type in a data set, then that's what you would have, and you have all the safety that goes with that. But if you just want to use the generic rows type, then you can just use a DataFrame. So that's where they're going with that. The other big one in 2.0 is some of these Tungsten further improvements, like whole query optimization. And I honestly can't think of any. Well, you mentioned the streaming stuff. They are sort of in this long-term trend of emphasizing DataFrames as the underpinnings of streaming. And one of the ways they're doing that is you'll be able to define like your streaming process. And then, no, sorry, I said this backwards. You'll be able to define like a DataFrame workflow. And then just by saying like persist to JDBC or stream from this source, you can turn it into a stream. So it'd be more of an integrated experience where it feels less like I'm setting up a stream and I'm going to do this in that stream. It'll be more like I'm setting up a data frame. Oh, now I want to stream it. It'll be sort of a philosophical flip in that way. But yeah. Anybody else? Maybe one more? Go ahead.
Two.
All right. Jeez.
So yeah, our last speaker just tipped off some information that the previous version of Tungsten used a lot of quasi-quotes, and recently they pretty much abandoned it and switched to a Java interpreter. Does that make you feel like they betrayed you, something like that? They should just backward about the interpreter optimization to quasi-quotes.
Yeah, no, that was probably a smart move actually, because quasi-quotes are still somewhat experimental. And what they've done instead is go to, I think they're using ASM.
Janino.
Yeah, that's right, Janino, which is poorly documented. I'm not really sure why, but anyway. So I think they made the smart move of and this has been a general trend, get rid of dependencies that are maybe not core to what we're trying to do. So I actually don't mind that one. They also took out Akka, because they weren't really using it that much. They were kind of using it as an RPC thing, so they wrote their own, which, we didn't like that, yeah, but I can understand why they made that choice.
Yeah, but is it Java? It's not Java.
Yeah, I know. Well, it's a bit weird, but when you get, in a way, Java is like a domain-specific language for assembly language or bytecode. You all know this joke, right, that Java is a domain-specific language for turning XML into stack traces? Maybe that's new to you as well.
Overflow.
Did you have a second question, or?
Yes. Well, I'm kind of interested in the reflection API. Do you think it's stable enough? I mean, it's already close to a feature freeze.
I think so. Most of the projects I've seen that use it a lot, like the type level family of projects, they seem to have figured out ways to write code that's even portable back to 2.10. So I think it's pretty safe to use it. Yeah, like anything, I would maybe firewall off what you're doing that's kind of edgy, so that if you had to change it later, you wouldn't have it just spread everywhere. But yeah, I've actually used it myself and haven't really had any issues.
I'm kind of suspicious, because a lot of new things still has like experimental tag, and type manifest still hasn't been deprecated.
Yeah, that's a really good question. I don't actually know why those haven't been yet. I would imagine in 2.12 some of that will be removed. You can actually look at the 2.12 builds and see. But I honestly don't know why they're still marked that. All right, thanks very much, everyone.